Okay, so we're going to do question 2.8. So we have a 140 liter rigid tank, and inside this tank we have 1 kilogram of superheated vapor at 2 megapascals. Now, again, like with the other question, they're giving us a volume, they're giving us a mass, so that should make us think right away about specific volume. But one thing to just be careful of is we're given the volume in liters. So a liter is 10 by 10 by 10 centimeters. So to convert it, we're going to end up with 0.14 cubic meters. So we have to make sure we remember to convert it. So again, we were given a volume, we're given a mass, so we can find the specific volume. And since it is a rigid tank, that specific volume is not going to change as we do the problem. As we heat it, cool it, it's going to be the same. So 0.14, and it's just 1 kilogram. So we obviously have 0.14 meters cubed per kilogram. That's our specific volume, and that will not change. Now, they're asking us to find the pressure, the temperature, and the quality at each state. So initially we're starting at superheated, where pressure is 2 megapascals. And then we're being cooled down to a temperature of 50. Okay, so let me just put that up there. So we don't know the temperature. Immediately we know the quality, right? Because they told us it's a superheated vapor. If it's a superheated vapor, that means the quality is 1, because there's no liquid component to it at all. It's completely vapor, so it's a quality of 1. But the temperature we have to find. Now, just as a side note, they tell us it's a superheated vapor explicitly, but if they didn't, it's okay, because we already have the pressure and the specific volume. So by going through the tables, we would eventually see which table to go to. But they tell us, so it's nice of them. Now let's go find that temperature, the first temperature. So going to the tables for superheated vapor, and 2 megapascals over here. How come I can't write on this? It's not letting me write. Outstanding. Okay, well, if you can see towards the middle of the screen and on the right, we have a 2 megapascal box, right? And we're looking for the specific volume, right? We're looking in terms of specific volume because we know the specific volume, and that's the first column of each box. So if we come back to the box, so it's sort of in the middle of the screen height-wise, and it's on the right, we go through the column and we see we don't have 0.14, but we do have 0.13857, and we do have 0.15120 at temperatures of 350 and 400 respectively. So we have to interpolate between them to find the actual, temperature that we want. So 0.13857 and 15120. So if we interpolate 350 degrees and 0.13127 and 4, I can't remember it by heart. 13857, 15120. 3857, 13857, 15120. Sorry about that. So we're going to interpolate between these two. So let's get the slope. It's going to be this guy minus this guy divided by 50, which is the difference between 400 and 350. So 0.15120 minus 0.13857 over 50. And that will give us 2.526 times 10 to the negative 4. That's our slope. We need to find our value of b, of course, so let's just choose a random point to substitute in. Let's take the second point. So y is 0.15120 equals our slope times x, which in this case is 400, plus b. So b equals B equals 0.05016. All right, so our equation is y equals 2.526 times 10 to the negative 4x plus 0.05, that's 05016. Now we know y, right? We know the specific volume is 0.14, so we're just solving for x. That's how we're doing this. And if we do that, we'll get a temperature of 355.66 degrees Celsius. That's our temperature 1. All right, and we already spoke about the quality, but now we're going to state 2. Now we don't know the pressure at state 2, but we're told the temperature. The temperature at state 2 is 50. So that kind of feels it's low temperature. I'd be very surprised if it's a superheated vapor still. So I'm going to go instead to the mixture table, and I'm going to see what that tells me. And let's see if it's a mixture. So let's go to the mixture tables. Here we go. Oh, I did something wrong. Come on, there we go. And I closed them, of course. So we go to the mixture tables, and we're looking for a temperature of 50. Oh, good. We're looking for a temperature of 50. And before we get too excited, we have to make sure that our assumption that it's a mixture is correct. And we see that we're sandwiched between 0.001012 and 12.03 because we're at 0.14. So we're good, we can use this. So we have to find, and by the way, immediately we can read off from the table that our pressure is 12.349 kilopascals. All right, so let's go here, 12.349 kilopascals. But our quality, well, what's our quality going to be? So if we go here, for some reason it took me back. Our quality, so we see this 0.001012 and 12.03. That's the entire range of specific volumes. We're much closer to the liquid, but what we're going to do is do our specific volume minus VF over Vg minus Vf. That's how you calculate the quality. Okay, so our specific volume is 0.14 minus their specific, the Vf, which is 0.001012, dividing that by the entire range of specific volumes, which is 12.03 minus 0.001012. Okay, and that gives us a quality of 0.011, well, 0.012. So as you can see, very low quality, still a mixture, but very low quality, 0.012. And just to write it down, what we were doing there is our quality. So 0.14 minus VF over VG minus VF. Okay, so again, if you picture it like a line here, which it is, we have VF, we have VG, where somewhere, we don't know exactly where, but quality is telling us how far along we are. So we're basically, we know this distance because these two values, VF and VG, are given in the table. We know our value because we just calculated it as 0.14. We know this guy. So we're just doing this here, and we find that it gives us a quality of 0.012. Okay.